Hi again everyone to this NPTEL course on machine learning for core engineering disciplines. In the last class we looked at clustering algorithms, and these are an important class of algorithms in unsupervised learning wherein you are trying to learn the underlying structure of the data set. So, whatever core engineering discipline you are belonging to, you may want to find similarities and dissimilarities between various data points. So, whether you are someone working in the field of fluid mechanics or someone who works more on molecular engineering or materials engineering, or you design processes that manufacture items, or you work with robotics. So, anyone, you may want to understand how your points are clustered in a feature space. So, that is where we started, and we looked at a very famous algorithm called K-means clustering, wherein based on the means of every cluster you then assign points to the cluster, and then the algorithm proceeds and at one point you converge. So, before ending the lecture I told you that the next time we will discuss on how we can determine the optimal number of clusters, and that is what that is where we will start with, and then subsequently we will move to other types of clustering. Okay. So, the first topic at hand is to determine the optimal number of clusters in K-means clustering. If I refresh your memory, we defined something known as the within cluster sum of squares, the WCSS, which is a measure of the variance within every cluster, and then we sum over all the clusters, and it is that metric we are looking to minimize as the clustering algorithm goes forward. We also discussed that in the extreme limit of the number of clusters k equaling the number of data points, the WCSS will be exactly equal to 0, because each point will be the mean of its own cluster, and therefore the WCSS will be 0. So, what we do to determine the optimal number of clusters is we plot the WCSS. So, this is the within cluster sum of squares, the WCSS as a function of the number of clusters k, okay. And you already know that the largest value of k is n, right. The largest value of k is n. So, n is the number of data points and as already discussed, if the number of clusters equals the number of data points, the WCSS is exactly equal to 0. So, that is the point on the x axis you can see, right. Alright, so when we start plotting the within cluster sum of squares, right, you will start with fewer and fewer clusters and then start increasing it. So, the data may look something like this. So, as you keep on increasing the number of clusters, the WCSS keeps on coming down, and of course it starts tapering, right. And you know that yeah, I think it will take some more time to taper. So, perhaps it keeps on falling like this, and at some point it just starts to taper, and you know that the lowest possible value is 0 when the number of clusters equals n, right. So, what we do in this kind of a plot, right, this is called an elbow plot, right, and we want to identify the elbow point, right, which is the point at which the WCSS saturates, right. So, it is keeping on dropping, right, and at some point, right, it just completely saturates. So, that is like an elbow, right, there is a sharp decline in the curvature, right, the slope at this point. So, you take this, right, as the optimal number of clusters. Obviously if the number of data points is same as the number of clusters, then you get a WCSS of 0, but that is not very useful, right. That is like saying every point is unique. Yes, every point is unique, but the whole idea was you can find some similarities and some differences. The other thing I want you to note, I mean, and this may not be very evident in the plot, there is perhaps a kink here, right. So the number of data points is huge, but the number of clusters we have been plotting, right, this is like 1, 2, 3, 4, 5 or 6 clusters. The way I have drawn it, let us say the optimal number of clusters is 6, but the number of data points can be in hundreds, thousands, 100,000s or even millions and larger, right. So I hope you notice that there is a kink here, and obviously the number of data points, right, is much larger than the number of clusters that you typically choose, right. So essentially from this elbow plot of the WCSS versus the number of clusters, the optimal number of clusters right is chosen at the elbow point at which the WCSS stops reducing significantly. Okay. So this is how you determine the number of clusters, and once you have the number of clusters you can then start to understand what is going on, right, within the data sets, why certain points are more similar to each other and why others are more distinct. And the way I discussed in the previous lecture, you can even develop different supervised learning models within each cluster. Maybe those models will work better than if you just had a model for the entire data set. So those are all strategies you can adopt. Okay. So this brings me to the end of the discussion on the K-means clustering. I will now move on to the next type of clustering that I want to cover, and this is called K-medoid clustering. Right. And in this clustering algorithm, instead of minimizing the sum of squared distances, so instead of minimizing the sum of squared distances to the mean of every cluster, we minimize the sum of distances to the most centrally located point called the medoid in each cluster. So notice here that this medoid is drawn from one of the data points, right. So unlike the K-means clustering, right, where you were determining the mean of every cluster. So in K-means, what was important was the mean of every cluster, and obviously this need not coincide with any data point. The mean is the mean, right, it can lie wherever in between any of the data points. However, notice what happens in K-medoid clustering. Here you are minimizing the sum of distances from the most centrally located point right, which is called the medoid. So, the medoid is drawn from one of the data points, right. So, we look at the medoid which is derived or which is one of the data points in the data set itself, right. So, in some sense you are giving more physical importance, right, to the actual data points themselves than to say that you will consider the mean of every cluster. So, that in a sense is what is happening in the K-medoid clustering, and because of the use of one of the data points from the data set itself, it is more robust to noise and outliers. So, thus K-medoid clustering is more robust to the presence of outliers and noise. Why? Because an outlier can greatly impact your mean, but that outlier would never be chosen as the medoid, right, because the medoid has to be drawn from the data set itself, from the cluster itself, and it has to be one of the most centrally located points. So, your outliers, right, can really disturb the mean because it can push the mean in one particular direction, but it cannot really change the medoid, and therefore the K-medoid clustering is more robust to the presence of outliers and noise. And if you would rather have your clusters be defined on one of the data points themselves, the data point that is more centrally located, then you should prefer K-medoid clustering over K-means clustering. Okay. So, how is this actually implemented? Let us see. So, this can be mathematically written as the minimum argument, right, corresponding to the choice of the clusters C1, C2 up to Ck. Again, there are K clusters, and then the medoids, the set of medoids M1, M2 up to Mk, right. So, these m's which were earlier referring to the means in K-means clustering, these are the medoids of each cluster. Okay. So, now again you sum over all the clusters j equals 1 to k, then you sum over all the points within each cluster. So, I goes from 1 to n, but xi must belong to the cluster j, and then you just minimize the sum of the distances between each point and the medoid, right. So, this Mj is the medoid, right, and you can also formally write what is Mj. Let's do that next. So, Mj can be written as argmin xi belongs to Cj sum q equals 1 to n, xq belongs to Cj, the distance between xi and xq. Okay. So, you are summing over all the q's and you are finding which point, right, it is that is most centrally located, right. So, this is how K-medoid clustering works, right, and it is very nice because in this case, because we are not really relying on the mean, right, we can use any sort of distance metric here. So, instead of the Euclidean distance, we are free to choose any other distance metric. So, apart from the Euclidean distance, any other distance metric can also be used in K-medoid clustering. right, because we are not relying on the centroid and the geometrical notions of the centroid. We can sort of move away from Euclidean distances. So, I just want to remind you how Euclidean distance or any other type of distance can be computed. So, let us look first at Euclidean distance. So, if you want the Euclidean distance or the usual distance that is defined between two points which are denoted as vectors, is some q going from 1 to the number of components, right. So, let us denote the number of components of the vector as nc, and then this goes from xq minus yq whole squared to the power 1/2, right. So, you already know this, right, you have encountered this, and I am just going to explain the notation here. This is the number of features, right, because you are working in feature space or the number of coordinates, right, which is part of every data point. So, you could have even called it p, because usually we are using p to represent the number of features, and then this q is the index used for each feature here. Okay, so that is Euclidean distance. The next distance is Chebyshev distance, right, and this is basically based on the maximum separation along any particular feature, right. So, if you did not really care about the total sort of distance, but only the maximum distance along any particular feature, say one feature is very important and you only want to know what is the maximum distance, right, along any of the features, then you could use this. So, this is defined as the maximum over all the features xq minus yq, right, with an absolute magnitude function. So, that is the Chebyshev distance, and finally there is something called taxi cab distance, right. So, this is when you are sort of having a grid of roads, right. So, let us say there is a grid of roads, and then on this grid, right, which are the roads, you can't really move in a diagonal direction. So, if you wanted to go from a point A to a point B, let us say here, the only way you can go is if you went along these roads, right. So, that is one way to reach B from A, but then the distance between them in the x and y components, that is just the sum of the respective distances, right, along each coordinate axis. So, using that in mind, you can write the taxi cab distance, right, which is also called city block distance, as sum q equals 1 to nc or p, number of features or number of components, xq minus yq, right. So, this is also called city block distance. Right, because what I have drawn here, I mean someone can envision it like a block of a city or a block layout of a city. These are the blocks, right, these are the blocks, and then you have roads in between the blocks. So, if you want to reach from a point A to a point B, then you have to go along these roads, and therefore, this makes sense. You want the distance along each coordinate, right, and then just sum that up, right. So, xq minus yq, that is the distance along every coordinate, and then you sum it, right. So, I hope this makes sense. Alright, one thing actually, so there is no need to put vector signs here on top of these, because obviously these are the components. So, the vector sign will only appear when you are referring to the full feature vector, but when you are referring to the individual components, then there is no need to put the vector sign on top of that. So, hope you have corrected that in your notes. Okay. All right. So, this is the basic gist of K-medoid clustering. How is this done, right? So, let us delve a little bit into that. So, the algorithm to achieve K-medoid clustering, that is called partitioning around medoids, PAM for short. Okay. So, how you do this is again the steps are somewhat similar. So, as K means clustering. So, first you initialize of K of the n points as the medoids. You randomly choose, right, any K of the n points as the medoids, then you assign each data point to the nearest medoid, and since there are only K medoids, you will have K clusters, and then you will swap the medoid of every cluster with another point in the cluster to reduce the total dissimilarity, right. If you remember, we had defined, right, this total dissimilarity here, and that is the whole objective of this particular algorithm. Okay. So, this is K-medoids clustering, and it is quite useful and interpretable because each medoid is a real point in the data set. So, it is more interpretable as every medoid is an actual point in the data set. Okay. So, I hope this makes sense. All right. So, the next clustering algorithm that I want to discuss, and that will be the last algorithm that we discuss in this course, is called density based spatial clustering of applications with noise. So, this is shortened to DBSCAN. Right. So, the nice thing about this algorithm is one does not need to specify the number of clusters, and you can find arbitrarily shaped clusters, and it is based on the argument that points, right, should be clustered based on how densely a certain region is packed, right, in terms of the number of data points lying there. So, the algorithm groups together points that lie closely packed and excludes those that lie separated by low density regions. Right. So, that is the way this density based spatial clustering works, which of course is made clear by the name of this algorithm as well. And like I already mentioned, unlike K-means and K-medoid clustering DBSCAN does not require the specification of the number of clusters. And it can find more arbitrarily shaped clusters. Okay. And that is because of the use of the density of the points as a way to cluster. So, therefore, the shape of the clusters is not really determined by any geometrical metric as in K-means clustering. Okay. So, let us see what does have to be specified. So, you do not have to specify the number of clusters, but you do have to specify other parameters, right, because how else would you then figure out how close these points are in terms of being closely packed or low density or packed with low density. Okay. So, the parameters that we need to specify are 2 in number, and these are epsilon and the minimum number of points, and epsilon is the maximum distance between 2 points to be considered as neighbors. Okay, so that is epsilon. So, if 2 points are more are spaced more than epsilon apart, then they are dissimilar and they will not be considered neighbors. And then this min points is the minimum number of points obviously within epsilon distance, the epsilon that was defined above to form a dense region. Okay, so, these are the 2 parameters that you have to specify, epsilon and min points, and together they will then determine, right, how many clusters are there and how many points are there in every cluster. So, then a point x in the data, and typically we have said that we are having real data, right. There are n data points and p features. So, r n comma p, r denotes the set of real numbers, is a core point if the number of points, right, and again I am using this notation, right, wherein the pipe vectors, they enclose the set, which means that the number of points in that set, that is what we are interested in. So, the number of points in the set y belongs to x such that the distance of x comma y is less than equal to epsilon, right. So, the number of points in this set should be greater than or equal to the minimum number of points, right. So, this is the gist of it. Of course, the algorithm to implement it is more complicated and we will not go into very much the details. And again, to reiterate, this pipe operator here, right, that encloses this set. So, it is denoting the number of points in the set, right. So, this is the set we are talking about. Okay. So, the advantages of DBSCAN are several, I mean some of them I have already alluded to. The first is that it removes requirement to choose k, right. Of course, the k can be chosen by the elbow plot like we just discussed, but it makes much more sense to think in terms of the distance in feature space, right, because when you have a data set you know, right, what kind of points are more dissimilar in terms of some kind of a distance metric. So it is better to work with those distance metrics, which you can specify that epsilon and the minimum number of points, and it can find arbitrarily shaped non-convex clusters, and it can also handle noise and outliers, although K-medoid clustering is also quite good at it, right. There are some limitations, and as you would have guessed, the limitations is that we need to have some feel of what epsilon and what minimum number of points is relevant. So algorithm requires us to specify epsilon and the minimum number of points, which is fine if you have a good feeling for how different points should behave or how similar points should behave in the data set, but in some cases this may not be known, right. So this brings me to the end of this lecture. In today's lecture we discussed the elbow plot to decide the optimal number of clusters, right, in k-means clustering. We also discussed about K-medoid clustering, in which instead of taking the centroid of every cluster we just pick one of the points in each cluster as the medoid, it is the most centrally located point, and this makes the algorithm more robust to outliers. Then we discussed this density based spatial clustering of applications with noise or DBSCAN, and here the focus shifted from the number of clusters, right, to essentially clustering based on how closely the points are located. So you had to specify a radius in which you were searching for points to belong to the same cluster and the minimum number of points to form a cluster, right. So I hope this discussion was useful for you, and I look forward to seeing you next time. Thank you for joining.